Good evening, everyone, and welcome to this session. We are located in the School of Mathematics, but we have a very strong connection with the School of Physics, so everything related to astrophysics is happening around these two schools. So it's my pleasure to introduce you my colleague, Dr. Phil Judge. We've been working together for the last 9 weeks here in Melbourne. Dr. Phil Judge is a senior scientist at the National Centre for Astrophysics, Atmospheric Research in Boulder, in Colorado. And Dr. Philip Judge has a PhD in astrophysics that was awarded in 1985 at Oxford University. So you'll recognize the British accent. Although he spent many years in the United States. So his research is mostly in solar and stellar physics. On a daily basis, he does spectroscopy and spectropolarimetry, so two important words for astrophysics, and plasma physics, in an effort to understand questions such as why is the sun obliged to change its spots? Do we know the answer to this question? Not yet. All right. So on the other hand, so you'll hear the science today, but I would like to tell you a few more things about him. He's a husband, and his wife is in the audience. Spot her. He's a father. He's a cancer survivor, amateur astronomer, part-time opera singer, a good one, and recently is an author of science fiction with the aim of communicating climate science to the general public. And his book is already on Amazon. I've started reading it. It's good. All right, so Are We Alone in the Universe by Dr. Phil Judge. He's going to have 45 minutes. At the end, we ask questions, right? Okay.
Thank you. Thank you, Alina. That's a very kind introduction. First, I want to say thank you to Alina for giving up her spot to allow me to speak. I'm only here for 9 weeks, and I don't know when you will get the chance to hear Alina again, but I strongly recommend you come when she does speak. I just want to say one thing about HAO. It was an institution, it's 75 years old, and some people have a theory that some institutions live about as long as a lifetime. So I hope that I'm not in a dying institution, but nevertheless, we're still going. It started in 1940. We started because of World War II. They wanted to know why they couldn't communicate with their ships at sea sometimes. And so did the Nazis. And the Nazis had an installation in Europe, and we had an installation in a place called Climax at 14,000 feet. That is the original high-altitude observatory. Now we've been demoted to about 5,500 feet in Boulder, Colorado, where there are many more restaurants and very little things like uranium and plutonium and things like that up in the mountains. Okay, so enough of my background. Are we alone in the universe? First of all, that's not a scientific question because you can't ever disprove it. But you might suspect it's so, and it might worry you. And it certainly worries me that we haven't heard from anybody yet. But in the tone of this thing, I want to give you a nice quote. That is an excellent question. I would hate to spoil it with an answer. And so let's get straight into it. So this is a story. The story's written, but much of it remains as yet unreadable to us. I'm going to tell you the story of life and of the universe in less than 50 minutes. This is manifestly an absurd thing to do. I mean, how can you do that? Not even Richard Attenborough can do that. But he's not a physicist, and physicists boil things down to very elementary things and ideas. And so some of you might think physics is hard, mathematics is hard. In some ways it is, because you have to deal with nasty things like equations and balancing things and all these things. But in many ways, physics is the simplest subject in science. We're just trying to look for cause and effect. And so I'm going to make an excuse. I'm going to give you a physicist's point of view of this question tonight. So you will see many naive things along the way, and I would appreciate it if you would just ask questions about clarification along the way and keep your more profound questions until the end so that somebody else in the audience can answer them. Perhaps only a physicist would be naive or dumb enough to actually attempt to try this. But anyway, let's go and see what happens. So the story starts 65 years ago. For those of you in the audience that are less than, well, the median age of most people these days, there were no orbital rockets at this time. The first flight of an orbit thing was 1957. And that was Sputnik, and that was way in the future. And people's idea of space was something like this. A wonderful picture of a very 1950s looking female, young female, a rather, could be any age, elderly female, and a rather cool looking dude here. I think he looks like he could be from Bondi Beach or something, if he'd had a nice board with him. But anyway, let's get to the more serious stuff. This is a picture of Enrico Fermi, who is very well known, one of the most famous physicists of the 20th century, Nobel laureate 1938. A whole area of physical statistics is named after him, for instance. And he was having lunch at Los Alamos, the bomb laboratory in 1950 in New Mexico. And this cartoon, I found the very cartoons they were looking at over lunchtime. And you can see the aliens with the toilet plungers on their heads, apparently, carrying garbage from New York into their spaceship and taking the cans back to New York. They wanted the New York garbage, apparently. This is important stuff for them. So the big question he came up with is, or the question he came up with that day was, where is everyone? Now, this has been since become known as the Fermi paradox, but there's a story even behind this story. And it's actually been written up by a chap called Eric Jones. And this is the account of Fermi's question, which I dug around and found this on the web. Fermi's famous question, that's so central to debates about the prevalence of extraterrestrial civilizations, arose during a luncheon conversation with these three characters, famous physicists all by themselves, Connor Pinsky, Edward Teller, and Herbert York. I found out while doing this that Herbert York has a little bit of the Mohican in him. He's Native American, and he looks a very daunting figure. I imagine him being about 6'8" tall, but I have no idea how tall he is. If he's 5'3", then I don't really worry too much. Anyway, this is an interesting, very interesting account of this, and it was put together by Eric Jones, and I've tried to find the pictures of the characters as we go along. This is an official report of Los Alamos, but it's not classified, so you know we can certainly. I'm not going to get in trouble here. This is interesting today. The Fermi paradox is not Fermi's, and it's not a paradox. Okay, so this is by a fellow by the name of Robert H. Gray that I could not find a photo of, but it was published as in January 29th as part of Scientific American Communications Online. So what's going on here? Well, in this report by Gray, both York and Teller seemed to think that Fermi was questioning the feasibility of interstellar travel. Nobody thought he was actually questioning whether there was life out there or not. So where does this leave us? Where does this Fermi paradox come from? Well, according to Gray, there are several parts to this. First of all, this is now many, many years later, a quarter century later. If extraterrestrial intelligent life exists, it would be here. Therefore, we are alone. He's basically saying that we've got so much time in the universe and so many, many stars and so many, many galaxies, surely somebody somewhere would be visiting us already and we should be seeing them. That's his argument. Later on, Frank Tipler, and this is known as the Hart-Tipler version of the Fermi paradox, he was worried that where would anybody get all the resources? So he said, well, you know, maybe it's not that unreasonable, actually, to travel around the universe and come to our particular boring star and see what's going on. He suggested a self-replicating universal constructor with intelligent comparison, et cetera, et cetera. So people are sort of, you know, getting into this stuff quasi-seriously. And then, in between this period, possible origin of the confusion, according to Gray, is in 1987, this physicist used the phrase Fermi paradox in a paper citing Hart's idea as one possible answer to Fermi's question. Namely, not really to Fermi's question, but now we have a situation a quarter century on where we are actually thinking hard about whether it's odd that we haven't heard from anybody or not. Okay, so that is the essence of the Fermi paradox. To talk about this, we have to define, first of all, so that's the introduction. We have to define, first of all, what is life. It turns out there's no agreement on what is life in amongst scientists. There are various forms of definitions, and I've given just 3 of them here. You can see this is a physicist definition, Darwinian evolution one, set of instructions. This is complexity theory. If you're interested in it, I put little things in here to find out more about this stuff. But the reason I mention this is because you can find little things that sort of disagree with this. For instance, a mule would certainly fit the definition of most people's definition of life, but it cannot have offspring. Therefore, it cannot go forward. A computer program contains many of these things, depending on how you define the organism. This was realized all the way back, the origin of the computer. And there's this, so there's all kinds of difficulties in actually defining what life is. I'm just going to assume that we know it when we see it. And it's got made up of biology as we know it. In spite of the fact that we don't know this, there is actually a well-defined piece of academic area called astrobiology. Now, as far as I'm concerned, there is no astrobiology, there's just biology. So what is astrobiology? It's about studying things like the energy source, the components that make up life, the building blocks of life, namely, as we know it, these self-replicating molecules, and then the macroscopic signs of life, the animals, the beasts, the various things in the universe that can sustain life. So astrobiology is actually looking forward as a magazine. It's in its, it's been around for at least a decade, and it's a fully respectable scientific refereed publication, and yet the subject doesn't exist, which I find pretty interesting myself. I guess we're optimists. Let's just take a step back then and look at what the ingredients are for life as we know it. Well, I know there are probably some school children in the audience. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, plus a bunch of others. These are the building blocks of the material that we found out when we looked at inside the structure of life through the history of biology. We certainly need these things to make what we know as a self-replicating molecule in a carbon-based life form. We also need a substrate in which to have this stuff being assembled. You can't have it frozen solid into a rock. You've got to have chemical reactions. So you have to have some warmth, some energy, and you have to have some mobility, which means for most of us water. It's an ideal substance to put most of these elements in so that chemistry can happen. Then we need a stable environment for giga-years. Anybody under 15 in the audience know what a giga-year is? Giga, gigabit, gigabyte. Yeah. Who's that? Yeah.
It's a small section of a computer.
Yeah. So you have a gigabyte of energy in your computer. That means 1,000 million of them. So you need about 1,000 million years to sort of stir things up and get them going and for the Earth to settle down. We know this much, okay? We also know that we need some stirring. It's got to be stable, but it can't be too stable. It's like making porridge. If you cook the porridge for Goldilocks, it's going to go to a clump in the bottom unless you stir it up. Same thing's true for life. You must have self-replicating molecules, RNA and DNA in this case, and then we must have little tiny things, bacteria, very, very simple, quote simple things, called prokaryotes, archaea and bacteria, and then we have eukaryotes that we're made of. These basically are single-cell organisms, the simplest forms of life you can find. Well, to a physicist, that's an enormously complicated thing. I mean, it's almost hopeless to study that from the first principles, right? And so a eukaryote, something like you or me or a rat or even a flea, is something that's, you know, even more complicated. So anyway, these are complex life, these are simple life. And then, even if you get that lot going, and you have the luck to get these kind of things going, you need a lot of evolutionary pressure for about a giga-year or two, another 1,000 million years, and you need to have abundant oxygen in order to build animals like us. You can, with bacteria, they kind of burp up, like yeast will produce by making alcohol, it will produce carbon dioxide. The various old organisms produce oxygen as they respire. But there needs to be a jump in the amount of oxygen to support real animals like us. And we'll get to that in just a moment. So here's the history of life on the Earth. And we're starting 4.5 billion years ago, because if we started before that, there wasn't any Earth to live on. Okay? And so what's going on is that pretty soon we start seeing water. It's not clear where that water came from either. And if you want to ask about that later, that's fine. The Earth actually lies in the dry zone. You have to bring it in with comets at some later date, because otherwise it's too dry. The earliest life pretty soon appeared. This is 1,000 million years. No, half a billion years here, when life first started appearing inside the oldest rocks we can find, some of them in Australia. And then what they call simple life started to occur, even when you had massive bombardments of the Earth by meteorites from the formation, left over from the formation of the solar system. And then these things started to produce trace amounts of oxygen 3,500 years ago. Okay. Now we go from 3.5 to 2,500, and finally we have a great oxygen 2 event. So all the little bacteria suddenly burp out all the oxygen, and the Earth, instead of being full of methane and other things, is now full of, got a lot of oxygen and nitrogen in it. It looks much more like it is today. And to make animals as big as us, we really must have this kind of size. We must have abundant oxygen. So this all happens by the time the Earth is a couple of billion years old. And then we get to the earliest sexual reproduction. So, you know, you talk about an old joke. The actress and the bishop jokes have been going on for about 1.5 billion years. So there aren't any new jokes under the sun. Explosion of things. So this is the history of Earth, and we are just the tiniest blink in the top here. That should tell you something about Fermi's paradox. We've only been here as humans for 100,000 years or a bit longer than that. There were people walking on this continent, and they survived various ice ages for 50,000 years. I find this absolutely amazing. And, but that's but the blink of an eye compared with the history of the Earth. So, and if you think about the time in which we've had these things, lasers, being able to make a tie, being able to have dentistry, that's only been in the last 200 years. I mean, that's one part of a tiny, tiny fraction of the age of the universe. So that says, yeah, if we're looking for life like us, the probability of us finding it in an advanced state depends on what we assume about our own future. One of the scenarios is, of course, the famous Neville Shute book, which I enjoyed very much as a young person. One of the most famous Australian authors, I don't need to tell you, I'm telling other people in the audience, on the beach. Are we capable of surviving the technology that we produce? I'll come back to that. What do we mean by simple life to a physicist? To a physicist, this is pretty simple, a hydrogen atom. We can solve that one. Dirac finally figured out, plus some quantum electrodynamics, how to do that in the 1930s, okay? We get to something like this. That's an empirical measurement. From ab initio, you would not produce an amino acid by physics. That's only 8 times the size of a hydrogen atom. That's because there's about 500 atoms, and to do that kind of calculation with a random collection of things and put them through a computer would be a very big search indeed. And you'd make so many errors on the way, it would be astonishing if you got anything. That would be quantum chemistry. We get to something like small bacteria. This is the number of atoms we've got. This is starting to get more healthy for us physicists, because once you get to a larger number, we can start using statistics. But then you think, oh, wait a minute. Life is something, if you saw the definition of Schrödinger, that works against the natural state of physics to go and kind of go blah. The universe kind of wants to die out. Life uses energy with its engines to drive towards a organized state, whereas physics wants you to get to a disorganized state. So statistical mechanics, as we call it in physics, starts to become valid when you have numbers like this. But we know that the essential ingredients of life are the things working against in spite of the statistical mechanics. So this is all biology. So that's just to give you an idea of what they mean by simple life. Most of us should know about what this is. These are a representation of what a strand of DNA looks like. These are individual atoms, and the lines represent the bonds between them in some symbolic sense. So you have on the order of 20 atoms in this thing here, and then this string can go on for, well, up to meters length when you combine things to encode the human genes, for instance. It's absolutely enormous. This thing, remember, is about 2,000 millionths of a meter across. But it could be 2,000 million times longer than that, the whole string of this stuff. Okay. So this was determined, this weird structure was determined by Watson, Crick, Wilkins, and Franklin in London, these guys in Cambridge. Curiously, these guys got the Nobel Prize for discovering this, and there's an interesting discussion, which many of you will have heard of, concerning whether Franklin deserved this as well. Interestingly, and this is something I just drop in because I couldn't help but do it, because I'm something of a feminist myself. No, I wouldn't put that, but she was described by Wilkins, her supervisor, as somewhat pushy and kept asking questions. And I'm like, my God, isn't that what scientists are supposed to do? I mean, what are you going to do, accept everything? No, she was right on the money, as far as I can tell, reading about her. So anyway. In case you think that's all theoretical, this is an ingenious experiment, 2012. This is silicon. Let's go back. This is silicon, this stuff. This is a strand of DNA. The technology people can do today is just astonishing. You blow it up, and here you see the DNA double helix structure in real life. Not a theoretical thing. I think that is an astonishing measurement. Okay. A physicist would then ask, okay, so we know what sort of life, and we know the things we need to do to make life work. Where will the ingredients come from? We're going to have to get, where did all this carbon, where did all the hydrogen come from? Where do we all come from? Well, we know that we come from stars, if you learn that much. But it's funny what's happened in our universe. So I'm going to look at the history of the universe. And what I'm going to do is, again, look at this plot. And I'll come over here this time for the people on this side of the room. This is what we looked at before. We looked from there to there, and then we looked from there to there. Now, this is when the Earth came together roughly 4.5 billion years ago. As we go down here, we get older and older, the North Star forms, Milky Way disk. So luckily, the Earth formed after the Milky Way, Andromeda Galaxy, and very, very old globular cluster, Omega Centauri, visible from here. These are the very, very, very earliest galaxies formed here. And this is in billions of years. So basically, nothing happened, and then the Earth was born and humans arrived for about 3 times as long. Okay, and you know, the wonderful thing about the internet is you can find all kinds of wonderful things. So I'm asking the question, where did these bits and pieces that make life come from? How did we get them? And is there something special about our universe that made it so? So here's a schematic map of the universe from 10 to the minus 43 seconds. That's called the Planck time. That's a dimensionless quantity at which we know the theories of Einstein and quantum mechanics break down. We don't know what space-time looks like. There are various theories about this that are going on right now, including brane theory, string theory, the quantum loop gravity. It's basically still a research area, but we have no idea what the physics is in this region below here. After that, we have things like strings. After that, well, what do we have? We have, that's the Planck time, before which we don't know anything. That's very important, because if somebody's asking the question, Stephen Hawking is, might ask the question, what happened before the Big Bang? And you have to find a way around this particular block, because we don't know what the physics is. You have to find a way around that without using the physics that we know, because there's no way to do that. And if you're willing to do that, you might come up with some conclusions about the origins of our universe. But to do that, you really have to ignore the physics that we know about. Or you really have to do something about physics we don't know about, more likely. Then there comes a little bit later on as it's expanding. So something's formed, and then it undergoes an enormous blow-up. It's like suddenly it starts off, and then somebody gets a balloon and pumps the bejesus out of this thing. So it's an enormous balloon, and it settles down again. And that balloon is needed in current models in order to make the cosmic ray background radiation as uniform as it is. It's remarkably uniform. And the only way they can do that, this is called inflation, and that's not in the standard model of the universe, so it's still a research area. But anyway, after that, we have these things here where the strong nuclear force is separated out. Gravity is not included in any of these theories, so gravity goes on and on forever without us knowing really what's going on. We know that the strong nuclear force separates out here. We have a quark-gluon plasma. That's just bits of stuff that's such high density. It's the stuff you build in the accelerators in the Earth, the Large Hadron Collider, all these things. And then, as you go on, it starts cooling down until you get things we recognize. But to go from there to there, we only end up with hydrogen, helium, and maybe a little bit lithium, beryllium and stuff, but no carbon or anything. And then we have a period of recombination period. So all the matter starts to be made up to 3 minutes. And then we have this period here where we're making atoms. See that? These are atoms with no charges on them. These are quarks and gluons. This is a hydrogen atom. It's got one proton or one electron around it. These are kind of condensed out of the cosmic soup. And then after another period of time, gravity has started to take over again, because the things are spread out so much. And when they spread out, gravity influences things from a long way away. So it starts to condense out things into galaxies and the first stars. And so you can see where we're going here. We can only get hydrogen and helium, a little bit of other things here. There's no carbon, nitrogen, oxygen. So this is where we come from these stars and things here. And then finally, here you've got the formation of RNA, DNA symbolically, and Archimedes, or whoever that's supposed to be there. So I want to just verify that this period after inflation, from here on out, is not just a theory. I mean, it is just a theory, if you like, but it's also, in accordance with science, compatible with some rather strong constraints. It is the simplest model. That's a good point. You really don't want to throw in models that are more complicated than they need to be. That provides a reasonably good account of the following properties of the cosmos: the existence of structure of the cosmic microwave background. That's an observed fact, 1950s. Large-scale structure and the distribution of galaxies. Abundances of hydrogen, deuterium, helium, and lithium. Those things all were forming in that period there. The accelerated expansion in the universe, et cetera, et cetera. So this is actually, in spite, if you look at this, we're going over 51 orders of magnitude. That's an inconceivably huge number in time. But that model more or less accounts for the large-scale properties of the universe as we know it. So it's a good place to start to understand how the things come from. And here's another way of looking at it. If you're a physicist, you would recognize a grand unification epoch when all the forces except gravity are joined together, electroweak epoch where the strong nuclear force has gone out, and then we get the quark epoch and the hadrons, and et cetera, et cetera. So basically, this is nearly a theory of everything from here on in, and it is nearly a theory of everything if you take into account the inflation, which people have postulated as well. Well, this model has 25 free parameters in it. There's about 20 in quantum physics, field theories, and what have you. And there's a further several to do with the large-scale structured universe, gravitational constant, speed of light, various other things. Okay? It has these number of free parameters and no quantum gravity, so it's not a consistent theory. It's a description of the universe that describes 3 out of the 4 forces that we know about. So you have to take that in mind. And you know, Einstein died trying to make a quantum gravity, of course, and many people have tried and failed, and there's been various claims of success and failures over the years. It's still a research area. What I want to point out are some curiosities, which some people would like to interpret in terms of evidence of a creator. Some people would say, no, it's evidence of some other things. But they are curiosities. Even for a physicist, they are definitely curiosities. Life in our universe requires some very specific values. So life in our universe, those things that we need, the Schnops elements, stable environment around stars, all this stuff. You go back to the beginning of the universe and you find out that all these forces need to be in a certain order for the universe to be the way it is. Even this weak nuclear force, which is sort of almost irrelevant, it basically just causes the decay of neutrons into protons and a neutrino and an electron. But even all these things, they need to be in a certain ratio, otherwise the universe the cookbook doesn't work right. It's like switching on the oven at 500 degrees instead of 200 and expecting your cake to come out very nicely. It's going to be cooked to shreds and you're not going to have anything to eat. There's a thing called a fine structure constant, which is basically a combination of quantum and large-scale parameters. No, quantum parameters here. That if it's off by 4%, you don't ever get any carbon, right? And therefore, because you get no fusion inside various kinds of stars, and there's no chemistry, the chemical and element abundances have to be in this kind of order. Helium is not so much important because it's chemically inert, really. But if there's too much of it, then it gets in the way, and you never get the reactions to happen in time. That's not the case. So all these things, they require these things to come in a line. And here are a few examples of what I'm talking about. From this period of time, if you have a change in the strong nuclear force relative to the other forces of about 4%, you don't get any hydrogen. If you have, in this period here, the free neutron lifetime is about 900 seconds. So somewhere in this period here, you fix the proton to neutron ratio. This is then fixed forever in the universe. And if you try and stick that stuff in stars, then what you've got here is a balance between expansion versus decay of the neutrons, and things freeze out. And it just happens that expansion balances things with the decay of the neutrons to be so, and we don't have an explanation for that. Some of these free parameters come in. There's one very, very famous one by Fred Hoyle, one of the most entertaining Yorkshiremen of his days, even more annoying than Jeff Boycott used to be to the Australian bowlers. Although, I guess Dennis Lilly, I have to say, was probably had the best of him every time I ever saw him bowl. So, anyway, Fred Hoyle made this prediction in 1953 that there had to be a resonance in the cross-section for this thing called the triple alpha process. Okay, this sounds awfully technical. You don't get any damn carbon at all, hardly, unless that is right there. The guys at the California laboratory went away a few weeks later and came back and found it, right where he said it was going to be. If that was off by a little bit, it would really change things for our universe. We have to have a balance between this lambda CDM. Lambda is the dark energy, cold dark matter universe. So it's a balance between the pushing out and the pulling in. Normally the cold dark matter only matters on small scales. This matters on cosmic scales. Okay, so we have basically a cosmological constant which has to balance the pulling back to make the expansion of the universe just right, so it doesn't go on forever and die out, or it doesn't, maybe it will, actually, that's sort of what we think it will do. It doesn't oscillate, etc., etc. We have a very peculiar thing, that molecules have awfully funny properties of water. I mean, ice floats to the surface, and everybody knows this, but that's rather unusual for a solidification process. And it's because of the distribution of charge around the hydrogen atoms and the polarization of the oxygen and hydrogen atoms in that substance, very peculiar. The balance between gravity and electrical force, the actual native forces pulling of gravity, which we have no theory for, it's just empirical, and electricity, which we do have a theory for, electrodynamics, that has to be about right for things like you and me to exist. Anything that you can see, anything microscopic, doesn't need this. But if you get sort of certain size, you have to have a certain ratio between the amount of force in gravity and the amount of force in chemistry to build animals like us to stand around and think. So all those things have to turn out to be sort of right. Generally speaking, then I summarize, small changes in the relative strength of the four fundamental interactions can greatly affect the universe's age, structure, capacity for life in particular. And if you're interested in this, just look on the web for a fine-tuned universe. Like I said, I'm not going to offer any answers to this question. I want to offer more questions. The universe today. Okay, so let's get down to it. 1961. We've got 11 years into this now. This guy had a famous equation named after him, and he organized a meeting for search for extraterrestrial intelligence. I shouldn't try and say that after a couple of large glasses of Foster's or something, I guess, but anyway. The SETI meeting, he put together an agenda, and he came up with this equation. Okay, so he's trying to figure out how many stars in the galaxy, given the rate of formation, et cetera, et cetera. So what are we looking at here? Okay. So he's saying, okay, we want to send radio messages. We've got these big radio telescopes. We may as well listen to people out there to see if there's anybody sending any, episodes of The Simpsons to us from their planet or something like this. Neighbors, maybe they're Southern Hemisphere people. This is the number of civilizations. So if you look at this thing, there's a bunch of dimensionless numbers, and this is a number, the number per unit time, the average rate of star formation in our galaxy. This is the length of time that civilizations send detectable signs into space. So what's this? Fraction of stars with planets, the number of planets that potentially support life. They've got to have water. They've got to have plate tectonics. They've got to have carbon, nitrogen, oxygen. They can't be gas giants like Jupiter. And then we have these things here. The fraction that can go to support life, that do go on to support life. Whoops. And then the number of intelligent beings, and then the number that really get to broadcast, signals. Okay. So this tells us an estimate. So let's have a quick look at this thing. In 1961, you come up with one galaxy, and remember there's about 10 to the 11 of these things in the universe. You end up with a number estimating between 20 and n, plugging in some numbers they had at the time. Okay? The big uncertainties are to do with how long, whether you can make intelligent life, and whether the intelligent life can actually, I think this one is probably on the order of 1 once you get here. Can you send lasers or radio signals? Probably on the order of 1. The fraction that can actually get started on life, that's a real biggie. Because you can take soup, mix it up, and it'll never come to life, but it has all the ingredients of life in it. Okay? What happens then in 2015, and I will show you how we measure these in a moment, the story becomes slightly less certain. You can see that we've got a bigger range here because I've taken the same numbers here. This number is really tied down. We know the star formation rate in our galaxy rather well now through measuring all kinds of wonderful things in astronomy. We know that there's potentially one planet per system that's going to be in the right place. The number that are Earths is about this number here. This comes from what I'll show you in a moment. We really have no clue as how life gets started. So this number is really a crapshoot, as they say in the States. And that never sounded very polite to me, being English, but they call it a crapshoot. Okay. But anyway, so this is where the Fermi paradox comes in, because if we take, say, the square root of the product of these two things, we get about the geometric mean, for those in the audience, you're going to get something on the order of about 10 to the 5. So there should be 100,000, 20,000 civilizations out in the galaxy sending messages to each other. But we've got to recognize that it could be as low as 3, and it could be as low as high as 300 million. So this is the essence of the problem here. We don't really know what the probability is of life getting started on a given planet, because we've only got one example of that. If we could go to Enceladus or Jupiter, Europa, and find that, that number would rapidly become somewhere up near 1. Okay? That's the magnitude of the work that should be done in planetary science, I think, in this area. And I'll have some solutions for this shortly. So much for the Drake equation. So potentially there's a lot of people out there that could be shooting things at us, and yet we've never heard anything from them. Never. Believe me, you would. And I'll show you one or two examples of these things, which I'm sure many of you are familiar with. Pressing the wrong button. One of the nice things is that you can find out one of these factors by simply measuring where the stars are relative to the planets. And there's the Goldilocks zone. Because I sort of said about gravity and chemistry, you want something about the size of Earth, and it has to be just around in here. We're assuming you have a main sequence star like the Sun that lives billions of years. Actually, there's a decent chance that life could start on a white dwarf for those amateur astronomers. You know what a white dwarf is. There's one right next to Sirius. If you have a 20-inch refractor, you can try and see it. It's a very difficult thing to see. But this guy here is in the Goldilocks zone. We're in the Goldilocks zone at the moment. And that's because we've got an atmosphere that keeps us warm, we've got oxygen, we've got bacteria, we've got everything we need here. So that's one way. If we could determine where these planets are around these stars, then we've got a way of doing this. So how do we do this? Well, you know that the Earth goes around the sun ever since Copernicus didn't get his head cut off. And so what happens is that the Earth doesn't go around the sun. They both go around a common center. And Jupiter's going around as well. So the sun wobbles. And if you looked at the sun, and this with Jupiter, which contains most of the mass in the thing, you would see the thing moving on the sky. So it would be like taking a picture of this thing. And if you had very, very powerful telescope, you'd see it wobbling. There's a star called Barnard's star, which does this, which has a companion. And this is a famous one. Most effective way of seeing this is to see the light. This is the Doppler effect. So here are two lines of sodium, like your street lights in the old days. And you would see these things going in frequency. They go, if the star could sing to you, that's what it would be doing. So we know by taking very accurate spectra what's going on. We can measure these lines. These lines are typically a kilometer a second or so across. We can measure things to about 1,000th of the width of the line, so about 1 meter a second. We can measure how fast these stars are going better than the accuracy that I can walk across the room. Isn't that amazing? I mean, some of these people have been awfully clever at doing this stuff. Okay. Another way is to watch an eclipse happen. So, just like the moon goes in front of the sun, the planets go in front of the stars. And it takes a dip out. But the planets are usually very small, so you take a tiny dip. If you have a lot of signal to noise, you can really do this very accurately. And this is, in fact, the way it's been done. And I want to show you some results, recent results from my friend and colleague, Travis Metcalf, who's also in Boulder, Colorado. Used to work with us at NCAR. And there is a question here. In the early days, before 2009, before the launch of a particular spacecraft, we had no idea about Earth. So all we had were these things. Well, this is pretty useless for answering the questions about life. So until 2009, we really didn't have much clue. Then along came this wonderful mission, Kepler. All it did was look at a very small piece of Cygnus about the size of your fist and sat there. Stars are out of focus, not in great focus, and just took data and data and data and data and data. And you sit there and you get a few 100,000 stars and you watch for these planets going in front. Then what do you get? You get thousands and thousands and thousands of these things. And you can see now we've got solid measurements of these things, again, capable of supporting the kind of life that we know about. We've answered that question through Kepler. One of the most amazing things is this work by Travis and his colleagues, a comparison of the planetary system of Kepler 444, this is one of the targets in the field, and our own solar system. I think you can see the similarity. This is just an artist's rendition. We have no idea what the surface of these planets look like, but nevertheless, we know they are there, we know they're that size, and we know how far away they are from the planets. This is a golden age. If there are children in the audience that are interested in doing astronomy and love this kind of thing, this is a great time to come into the field, I think. Astrobiology is really going to be something to be worth looking for. So how are we going to find this, given what we know? Well, I think we have to look for very simple life, and then we need to look for intelligent life in two very different ways. My feeling is that perhaps we have quite a good shot here at measuring this simple bacteriological kind of life, or signs for it. The best shots we have, I think, are within our own solar system, and many of you astronomers will already know this. Jupiter and Saturn have moons around them that have oceans. Jupiter is pretty close. The ocean's beneath the surface. It sits in the debris of Io, which spits out volcanic material from time to time. So if you go there with a spacecraft and measure stuff, you're never quite sure which satellite stuff you're measuring. There are occasional plumes coming out of Europa, and I'll show you one shortly. If we could measure with spectra what's inside that plume, we might find signs of molecular life living in the ocean underneath. The problem is it's underneath the surface. What we want is to get underneath it. So we'll either have to fly there and drill holes in it, which Arthur C. Clarke said is a no-no. You can't do that. All these worlds are yours except Europa. Or you take advantage of the fact that sometimes the surface is ruptured and it emits geysers of material out into its atmosphere. Then you've got to try and measure that. So I'm going to make a suggestion on how we might do that. Enceladus has a whole bunch of geysers. This thing is going crazy. Wonderful mission called Cassini that's still going around. So one idea I have is that given that these subsurface oceans, they've got a hard core, they've got liquid water underneath. This is a great place. They've got plenty of energy, because if there's water, it's warm. There's plenty of energy from the tidal interactions. This is a wonderful place that we might find some of this stuff. And so I think we might try something really difficult, but fun. And that is, imagine you've got a planet here, and this satellite goes in front of the planet, and it spits out a pile of garbage. Then what we want to do is observe the pile of garbage as it's coming out. And using spectroscopy, we can figure out the molecular makeup of that thing. And if we could find both, say, molecular oxygen and methane, which we won't in this case, but in stars we might, that would be a sure sign of life, because, boy, those two don't exist together unless it's out of chemical equilibrium. And the only way we know how to do that is through some kind of life, either with engines that we build or just our own metabolisms and the metabolisms of other creatures. This, I hope you can see these little guys here. You see these? And there's another one here. This is Titan. This is Enceladus Dione Mimas. So there they go. So as they're going across, you can imagine fountains spewing out at the top of this thing. This is the Hubble Space Telescope image, which is why it's so good. Let's imagine observing that during an episode where there's a plume. This is perhaps a one-off event. They think a meteorite hit the surface of this thing, and they managed to capture this bunch of stuff with the Hubble Space Telescope. And you can see how crude the observations are, because this is a small feature a long way away. Imagine, though, the light from behind the star shining through that. We should be able to get the molecular imprints of this stuff and see some forms of life. I think that's worth trying from Earth. If not the Earth, then a nice big infrared telescope. This is a fantastic system, this one here. If you haven't looked at Enceladus online and you want to get some imagination of what it's like to be on another planet, Cassini orbiter went past this thing and through some of these plumes. And you can see these things here. This is not scattered light like in your badly focused telescope. But what it is it's material pumping out from the surface in these geysers. See those? There are cracks in the surface, and this stuff is spewing out. This gives us hope in one way, in that if you know the orbital position of these things, and you know the orbit, you can wait until it lines up for you to exactly get your spectrum of the star, of the planet behind, through this stuff along a line, and then you really increase your path length. You should be able to see dips in the spectrum much easier. This is a very challenging observation because these things are very small. So what I would propose is the following. Let's go for this. Put your spectrograph slit here and follow the orbit of the satellite along until it comes onto the disk. So you keep taking data. The moment it hits the disk, you start analyzing these data, and you keep integrating, you keep integrating, you keep integrating. And if there's a plume that's there for more than an hour or two, it will add up, and it will be possible to do differential measurements all the way across the disk of the planet, even while the planet's rotating, and really try to pull out very high signal-to-noise signals. So that, I'm quite hopeful that might be something we can do. There's a catch-22 situation. Europa transits very often, but it rarely produces plumes. Enceladus will not transit until 2023, until the rings are flat again. But the good thing is, Cassini is still at Saturn, and we will have the James Webb Space Telescope. At some enormous cost, but we will have that, and that's a perfect machine for looking at these kind of things. Okay, we'll get into that in just a moment. On distant stars, we can do the same thing. We have a star there instead, and here's the planet, and here's the atmosphere. And let me show you what is maybe a unique signature of life. This is actually a computed spectrum of the Earth, and it's been checked against what you can see from the Cassini orbiter over in, when you look at the Earth separate from the Sun. So if you could block the Sun off somehow, this is what you would see. If you have this, as well as that, then that's a pretty good sign the chemistry is out of equilibrium and you've got some form of life. Okay? All right. Okay. Again, this is a spectrum of Venus, which we know has no free oxygen in its atmosphere at all. There's a spectrum of the Earth. These are calculated by, modern sophisticated programs. This is parts per million. What does that mean? Oops. It means that you better have parts per million. If you want to observe 1 part per million with a signal to noise of 1, you have to get a million counts on your detector. But we've got lots of time to do this. And lots of light eventually with the really big telescopes that we have. So it's not impossible that this can be done. And that's what some groups have been trying to do. I'll be wrapping up very shortly. So looking for intelligent life, you can use the radio search for extraterrestrial intelligence. I will simply say that so far this is in the realm of fiction, but people have been looking quite hard, and it's disconcerting that we haven't heard anything if you believe the higher numbers at the end of the Drake equation. And let's look at another way of doing it. Well, the radio SETI, there's a lesson to be learned, and that is, of course, from 1968, when student Jocelyn Bell-Burnell, as she got later known, when she got married, discovered this annoying thing going once a second in the sky that wouldn't go away. Hewish said, well, forget it, get on with some useful work instead. She wouldn't give it up, and eventually it turned out to be the discovery of pulsars. And I can't help but point out that these guys got the Nobel Prize for radio physics, and of course Jocelyn Bell-Burnell did not. Fred Hoyle vocally criticized the decision of the Nobel Committee for this, and he also did not get a Nobel Prize, even though he made that wonderful prediction in 1953, and people like Fowler felt like perhaps he should. Okay. Optical SETI. Lasers, believe it or not, are powerful enough to communicate between stars. I suggested that long ago. And this is how you do it. You simply make sure your laser beam divergence is very small by using a big telescope. So you give a very narrow beam. It's so narrow, in fact, that if you shoot it at a star, you might miss the planet nearby. So this is a sophisticated thing that you can do, but you better be careful with it. How can let's look at this. This has actually been started, and again, negative results. So they're looking for little blips of light. With current technology that you could build on the Earth right now, you put a big old 10 megawatt bursting laser on the front end of a 8-meter telescope and you send them out into space, we would be able to see ourselves quite a few parsecs away. Not been seen. Okay? Where does that leave us? Interstellar second guessing. Why I hope the search for extraterrestrial life finds nothing. I find this a little bit disturbing because not only are people that maybe you haven't heard of talking about this, and then people talking about a cloaking device. So you make it look like your planet isn't going in front of a star by shining lasers at the right time to make it look like there's no life here. And instead, even people like Stephen Hawking worry about, which is certainly someone not to ignore, worry about actually us really making contact with aliens. And I don't know how I feel about this personally. It makes me uncomfortable not to do research and not to push the limits to find out what's out there. That's all I can say, really. It's more a question of alien psychology than anything else, for which that makes astrobiology look like an ancient, well-founded subject. Okay. But it's a serious thing. To finish the story then, I said I wouldn't answer any questions, but I hope I've introduced some things that you perhaps didn't know, or perhaps you were amused by a little bit. The story is written, but most of it remains as yet unreadable. I've given you a physicist's point of view. It's been unfolding quickly, and it will continue to do so. But what are we to do if we actually become convinced we are alone? Why is that? What does that tell us? I think we probably will have an answer if Enceladus and the other Europa don't show anything in the next 10 or 20 years, I think it's going to be pointing in a direction that says life is actually rather rare to get started. And so perhaps we really are alone in the entire universe. That'd be kind of depressing. And if we are not alone, we will know that for sure, because we will find it. But what also will that mean for us psychologically? I don't know. I think it's probably a very good thing in the end. The future then, Kepler. This is a super Kepler looking over all over the place. This is the James Webb Space Telescope. This is the size of a tennis court, and it will be taking data all over the sky, according to the best proposals. And I would certainly like to see them look at these two satellites of Jupiter and Saturn to try and find these things. If you want more food for thought, I have a shameless ad for my book here, which is about climate fiction. There are a couple of professors here that are very involved with this, actually. And it's a climate fiction with a scientific bent, and there's two more. This one's finished. This one is almost finished. But most importantly, I would like to thank my host, Alina Donea, and her lovely daughter, Laura, not only for hosting me at the Mass Department here, but also hosting me at her house. And I'd like to thank thoughtCli-Fi for taking this fantastic picture of them. Paul's a professor in the Mass Department over there. Thank you very much for your time.
Thank you very much, Phil. Time for questions, I think. And I need someone to run this thing.
Yeah.
Anyone?
You talked about the Earth came after the, let's say, the birth of the Milky Way, and so you would assume a lot of other planets did the same. And given the distances, we've only been, how long have we been transmitting data from Earth out? What, 100 years? So it's only travelled 100 light years away. And given the distances of the Milky Way, how could we possibly expect to have received something already? You know, I mean, they could be transmitting themselves, but it's the distances might only be, say, 1,000 light years away, which is still 100,000 light years away from us.
So that's the last term in the Drake equation. That's the length of time that a civilization has been around to transmit things. That number for us happens to be about 50 or 100 years, as you're saying, absolutely correctly. For any other species, it could be 10 to the, if that species survives technological development for 10 to the 9 years, that's 10 to the 9 years. We've only developed in the last 100 years that capability. But if there's another species on planet X that's been doing it for, 10 to the 3, 10 to the 4, 10, so that number we put as 10 to the 3 to 10 to the 7 in the Drake equation. That number 10 to the 3 is assuming that we've blown ourselves up, or we've had catastrophic climate change, or we've had, a failure of antibiotics, and we've destroyed ourselves. I mean, there's all kinds of wonderful movies that have been made about this kind of stuff. But so that's a major question. What happens? And to put it in, if you're interested in this subject, I suggest you look for something called the Great, not the Great Divide, I had it here. The Great Filter. So the Great Filter is the time at which something happens in between the beginning of the Big Bang and getting to advanced life, or even after that. If the filter happens before that, for instance, there's an act of God, a collision of an enormous moon with the Earth that destroyed everything 1 million years ago, then we wouldn't be here sending transmissions out. And if, on the other hand, the Great Filter, we haven't got to it yet, namely there is an asteroid with our name on it coming for us, or there is, a Donald Trump with his finger on the nuclear button going to blow everybody up. You know, I mean, no, seriously. I mean, this is the kind of thing that one has to take into account when discussing this. Did I explain that?
Yeah.
Okay.
And haven't we received one signal that we can't explain?
The latest thing I looked at was this funny Kepler object, which shows this light going in front of it. There's this mega structure around this star, and they don't know what that is. It makes this, it's a big thing next to a planet or in the system, which is not a planet, it's something else. It seems coherent in some way, and they wonder if this thing is actually like this Dyson sphere idea, like an enormous thing collecting the energy from the star that an advanced civilization might have built. But that's just one of many, many, many more natural possibilities that have to be eliminated first. But yes, I don't believe there is a single piece of evidence. I mean, the little green men with the pulsars was a facetious comment, but you know, at that time they thought, what can we do to disprove this idea that it's really little green men? And of course, you know, you think to yourself, it's a very regular pulsing thing. It's going once a second. You know, well, I don't know any star that's going that fast, but maybe a collapsing star. You know, if it comes down, angular momentum, it spins up. And so that's turned out to be what it was in the end, and that's why, partly why Hewish got the Nobel Prize.
I'm talking about that signal, they called it the WOW signal.
The which?
WOW, W-O-W.
I don't know.
They received a signal, and it was unique, and they analysed it, and he put a little exclamation mark next to it, and he said, wow. Okay. Because it was, that was one signal, but they've gone back there and the same region, and they've never received a signal like that.
Science has to, I don't think there is a real methodology in science, but if there is a component to it that's very, very important, it's reproducibility. So that then would fail the credibility test for most scientists. Okay. So
and just one last question, and this is the stupid question now. This is the unscientific one. You know, we talk about, I mean, what we know and how we've advanced, what has been in the last really 200 years, where we question ourselves and the universe, and what we really know in 200 years is so limited compared to, say, a civilization that would be thousands of years old. And one of the things you put up on your slide is, you know, we would be visited by now if there was no. Well, how do we know we haven't been? And the only reason why I asked that is because just a week ago there was this story that I didn't even know about till a week ago, 50th anniversary of that Westall incident. I don't know if you've heard of that. And I just find that an amazing story and the cover-up behind it, and you think, what's going on?
Yeah.
So, you know, as a scientist that you are, what's your view on it?
Well, you have to have healthy skepticism is a terribly important part of science. And actually, if I can just plug one thing for the climate scientists, it's very difficult for a climate scientist to be told that there are skeptics, because the biggest skeptics I know of climate science are the climate scientists themselves, and I work in an institution that does climate science. So, but aside from that, you just have to be skeptical, and you need to ask for reproducibility, and you know, do your best to cross out natural options one by one. As to the finding of alien artifacts on the Earth, I don't know what we would even consider. I mean, I would imagine when the English first arrived in Australia, they found the Aboriginal stuff to be totally alien. I mean, that doesn't mean they come from another planet. So I don't know. If you find advanced materials, fully assembled electronic computer buried at the bottom of a pyramid, it's been there for, you know, 10,000 years, sure, why not? But then I'd still say, how the hell did they manage to get there to pull off the prank? No, these are sociological questions which are fascinating. I mean, scientists are humans. Let's not forget that. And we make mistakes, and we try and be critical, but really it's a human endeavor, and it's a lot of fun, and honestly, it's a real privilege to do research. And I really have enjoyed talking about this tonight, because it's something I've always wanted to do, and I'm surprised that you're all sitting there quietly saying, oh yeah, this is just another another boring. Do you think this is boring? You should hear my talks on solar physics. Yeah.
When you talk about the plume transiting in front of Jupiter,
yeah,
and that you're going away, just to clarify, is it the spectrum of Jupiter that's going to be the reference spectrum?
So what you do is, you know, that's going to be changing, because the clouds will be moving and all those things. So you would have to do a very clever slitless spectroscopy kind of thing, a fiber-fed spectroscopy, and do very careful differential measurements and try to find evidence for these things. And I think it could be done. I've done the sums. And there's enough opacity in these plumes to see that.
And just a dumb question.
Yeah.
Could you not use the spectrum from a star instead of waiting for it to transfer in front of Jupiter?
Yeah, indeed. Yes.
Use the star that's in the background that you know the spectroscopy of, and use that as a transfer.
Yeah. The trouble is that the moons of Jupiter and Saturn and the plumes are such tiny things that the chances of them going over in front of a bright star is incredibly low. I mean, for instance, the moon only travels in the ecliptic, but it only goes across Aldebaran, one of the brightest stars in the sky, once every, I don't know, 50 years or something. It's just a tall order. Yeah.
Hi, this is a question from a political scientist, and just from what I've picked up here. So, you said that one of the sort of great rules of science is reproducibility of an experiment, right? But you also said that in the search for extraterrestrial life, we have a sample grouping of 1. So why do scientists assume that life will develop in other places the same way it has here?
So there is spectral evidence for amino acids in space. I mean, if you look at certain molecular cloud structures in astronomy, I don't know anything about this except that I know this to be a fact. So clearly the building blocks of life are a natural, either a natural phenomenon or an unnatural phenomenon that's got built by some other alien or something. I mean, it's possible that we were planted here by some aliens who went off to another galaxy or something, right? I mean, some people even think that we might actually be just part of a big cosmic computer program, that you and I don't actually exist. We're all in somebody's computer code somewhere. I think that's a bit depressing. But so that's a very extreme value. But no, your question is a valid one. The components of life are everywhere. I mean, the first stars blew up and they smothered us with carbon, nitrogen, oxygen, fluorine, neon, magnesium, sodium, all the stuff we need, and all the way to iron. And then the other stars made the more heavy elements all the way out to uranium. So the bits and pieces lying around in there, and they've been assembled at some point in space as well as on Earth. So it seems very likely to me that it does make sense to make a study of astrobiology. Now, SETI, on the other hand, the search for real extraterrestrial intelligence, you know, for little green men with the things on their heads, that has been shut down by governments, and perhaps that's the right thing to do. I mean, you can only afford to do a certain amount of research with the money and resources you've got, and I think it's important for that research to serve the community that they're funded by. I mean, it's a real privilege for us to do this work, right? I mean, it's, honest to God, we're very fortunate to have this opportunity to do it. Yeah.
Just a bit on that again, I guess. The other day I read an article on a paper about how they statistically spoke about what life would be like possibly on another planet, and they used don't remember the exact terms, groupings. So like how, say, using football or soccer teams, they're like, if you I went around asking people, they would generally be like, say, part of the bigger groups, so that have like a few million or fans or whatever. But if you look at the actual football teams, a lot of them don't have that many fans. And I guess they used that sort of thinking on the Earth. So like, where would be the large football team that the most people are in? And then the other planets would be the groups that aren't as big. And I guess they went, well, then it's possible that the other planets that had life would be, say, smaller than Earth. So the creatures would be larger, and say the atmospheres would be darker and that sort of stuff like that.
So if I understand the question, the thing you talked about before was counting fans twice or something?
Yeah. So
you overestimate the actual number of people watching football by asking individual teams how many fans they've got instead of the actual number of fans supporting all football? Yeah. Okay, then I think the statistics is more sound than that in astronomy. I mean, one of the things that the Kepler team has to do extremely, extremely well, they're only looking at that much of the sky. Well, that's like a thousandth of the whole sky. So you've got to be able to say what your errors are in your numbers there in order to extrapolate over the whole sky. And my guess is that the statistics done in that kind of astronomy is so well understood because it's been done for 150 years or more that you're not going to be off by very much. And so you've got 100,000 stars there. That, in my naive view, is the square root of 100,000 is 1 over 300. So you're within 0.3% of getting the right answer for the whole sky. That would be my answer.
Cool. And just another question.
Yeah.
Not really about this particularly, but you as a scientist, like a bit of like, I guess what you do as your job, like a bit of what you do to like someone who's thinking about following a career in science.
Okay, sure. Yeah. So on a daily basis, you know, as a solar physicist studying that thing over there, and literally studying this thing here, this is the solar corona, we would be looking with very sensitive instruments at what causes this stuff to be very bright and very hot using computers and data from telescopes on the ground. So I would have gone to an observatory for a week, and I would have sat with the telescope people, and we would have got the thing set up, got all the adaptive optics working, the spectrographs set up, get all the images set up, start taking data and trying to understand what, for instance, leads to a solar flare. And then with Alina, we would then work with data like this from space, because we have wonderful spacecraft looking at these things all the time now. And you can tie all these things together and look for cause and effect. So as a physicist, we're always sort of looking for cause and effect. You know, if you see something very big blowing up on the sun, and then you see some junk falling down over here afterwards, and then you see another thing blow up, and you see some junk falling, you're pretty sure that the junk has come from the thing that's blown up. It's often a simple question like that. Now, in terms of the theoretical part, it gets a lot more complicated, because what you tend to do is make idealized models, or you make computer simulations of less idealized or more idealized models. And so part of the job is also sitting and synthesizing that. I mean, just trying to make a picture of that out of the computer box, comparing them and seeing where they're different so you can learn more about how the sun works. And I think that's fairly typical. So most of the time is spent on the computer. Much of the time is spent reading research articles, some fraction of the time, a small fraction of the time writing. I'm fortunate I don't have to teach. The guys here do an awful lot of teaching, which is not the same thing as a lot of awful teaching, obviously. They do an awful lot of teaching, good teaching for the engineering department in particular. And so they would have much more than that than I do. But yes, observing, simulating, measuring, and then writing proposals to get time on the Hubble Space Telescope on the different things, sitting on committees to do this kind of thing where you're judging other people's work or judging whether we should do this kind of research or that. Yeah. It's a wonderful privilege, and I really encourage anybody interested in it to do it, because, and I'll tell you one thing for sure, the people that succeed are the ones that really want to. That you will have a certain amount of talent that you need to have, but you already have that if you've got into college, I think, generally speaking. And if you're bound and determined to do it, I bet you will succeed. That's the thing. That's what separated me out from some of my colleagues who were, frankly, much cleverer than I was.
I don't need a microphone. Can you answer the first question?
Yeah.
Can you answer the first question that Dr. Helena proposed before you started?
What was that?
About the...
Where are we going for beers or something? Or?
No, she proposed something about why the sunspots rises.
Oh, my God. Yes. Okay. Let me tell you something really weird. If you look at the natural time scale...
Keep it short in the interest.
Okay. If you look at the natural time... This is all magnetism here, these bright things. These are all associated with sunspots, these little bright bits. If you look at the natural time scale in the physics that we really understand, it's called, and you put it into a framework which we know is going to be applicable to the sun, called magnetohydrodynamics. The sun shouldn't change on a time scale shorter than about 100,000 years, or 10 to the 5 years or so. And yet the sun's magnetic field not only produces spots, which is magnetic field coming once every couple of months or something, but the whole global field of the sun, I don't know if you guys know this, it changes sign every 11 years. And then it changes sign again every 11. The sun is huge. How does it do that? Our planet only does it once every 100,000 years or something. We've got a molten iron core, so it moves much more slowly. But the sun doesn't have any business doing that, according to what we know about the essential laws of physics. The difference comes in when you notice that the sun is a complex system determined by non-linear equations, and the physics we need to put in demands something about the microphysics that's different from what we understand completely. And that thing is the same thing that will cause you to feel very ill when you fly into Sydney Airport on a very bumpy ride. It's called turbulence. And turbulence is precisely part of the problem as to why we don't understand how the sun changes its magnetic field every 11 years. That's the best answer I can give.
Phil, thank you very much. And a small gift for you as well.
Oh, wonderful.
Thank you all for coming. I hope to see you next time, May 10th.